In today's problem, we're going to look at two more examples of homomorphisms, this time dealing with infinite groups, in particular, homomorphisms of groups of functions. And so the first one I have for you is called an evaluation homomorphism, or just an evaluation map for short. This is the homomorphism from the set of functions on R to R, which takes a function and evaluates it at a number. We're going to choose the number 0 because that's a very easy number to talk about and study. Makes for a good example. And the question is to see that this is a homomorphism and also to see what its kernel is. So let's remind ourselves, kernel equals the set of elements mapping to the neutral element. In this case, the neutral element of R is 0. So to see that this is a homomorphism, if I call this thing phi, I have to see that phi of f plus g equals phi of f plus phi of g, because the operation on the group f of r is addition. So this says to take f plus g and evaluate it at 0. This says to take f and evaluate it at 0. This tells me to take g and evaluate it at 0. And these two things are equal exactly by definition. This is how we defined the group operation on f, capital F that is. How convenient. Okay, so we see that it is a homomorphism. The kernel is the set of things that map to 0. Well, right now, everything is being mapped to f of 0. So the kernel is exactly those things that have f of 0 equals 0. Now, since these are fully general functions, these could be as complicated or messed up as you can possibly imagine. But if you're thinking about the subgroup of nice functions, like polynomials or power series from calculus or whatever, then this would mean that there's no constant term. That's a very simple way to think about what's going on. But please don't forget, like I said, that these could be arbitrary functions. So it's a good thing to keep in mind, possibly an oversimplification. The next example I want to show hones in on that idea. And now we look at so-called differentiable functions on R. And I'm going to use the fancy D notation for the collection of differentiable functions. And here, the simplest homomorphism, sorry about that. I pushed a button and it tabbed away. The simplest homomorphism on differentiable functions is to take a differentiable function and send it to its derivative. Okay, so again, we have to see that this is a homomorphism. I don't feel the need to use the symbol phi for this. We usually use the letter capital but print D for the derivative as an operator. So I'll do that here. I need to see that d of f plus g equals d of f plus d of g. And this is a basic calculus fact. Without going through the whole story, we remind ourselves that the derivative is defined by the limit h to 0 of f of x plus h minus f of x over h. I need to see that that's true We're a little hurting for space. Let me see if I can squeeze it in. Definitely not if I write that big. All right, just barely. We managed to squeeze it in. The important thing is this is true because when each of these limits exist, it's a basic fact that the limit of the sum is the sum of the limits when both limits exist. Both of these are differentiable. So this works and we're happy. So it's a kernel, sorry, it's a homomorphism because of our basic calculus experience. What is the kernel? Well, the kernel is the set of things that map to 0. The 0 element the neutral element of f of r is the zero function. So in other words, we're asking ourselves which functions have their derivative identically zero. And we might recall from calculus the functions whose derivatives always exist and are zero are exactly the constant functions. And I'll let you guys, dust off why that may be the case. Not a very difficult proof, but the calculus is a little bit outside our domain of abstract algebra here. And I think this is getting long enough for a practice problem video. Just the goal of identifying kernels of interesting homomorphisms. Hopefully we've done that here.